Good evening, everyone. My name is Andrew Fracknoy. I'm the chair of the astronomy department here at Foothill College in Los Altos, and it's a pleasure for me to welcome everyone here in the crowded Smithwick Auditorium and everyone watching us on the web to this lecture in the 17th annual Silicon Valley Astronomy Lectures. These programs are co-sponsored by the Foothill College Astronomy Department, by the SETI Institute, the Astronomical Society of the Pacific, and NASA's Ames Research Center, and we're very grateful for their support. This evening's program, we usually have superb speakers talking about sexy topics in astronomy, but we're especially fortunate tonight to have Dr. Andrea Ghez, who is professor of physics and astronomy, and who holds an endowed chair in astrophysics at UCLA, and is one of the world's leading experts in observational astrophysics. She heads UCLA's Galactic Center group. She has received numerous honors and awards, including the Crafoord Prize in Astronomy from the Royal Swedish Academy of Science, which is sort of our version of the Nobel Prize, a Bakerian Medal from the Royal Society of London, a MacArthur Fellowship, election to the National Academy of Sciences, to the American Academy of Sciences, and to the American Philosophical Society. She's very involved with the two giant telescopes that are bringing us news from the universe, the Keck telescopes and the still planned 30-meter telescope. But we're especially fortunate as listeners because she's very committed to the communication of science to the public and to inspiring young girls into science. And many of us have seen her wonderful talks and TED Talks all over the web. So we were able to lure her from Southern California with a little help from our gracious donor, who's now allowing us to have people travel for these lectures, which we're delighted to have. And so it is for me both a personal pleasure and a professional privilege to introduce to you Dr. Andrea Ghez.
Thank you. It's a pleasure to be here this evening and speaking at Foothill College and part of this wonderful series. I thought I would start off sharing with you how I enjoy starting off a class at UCLA. I usually ask the students to share with me something interesting about themselves and what they like about UCLA. And I get to learn all sorts of interesting things. But then I share with them why I came to UCLA. And it's this telescope. This is the largest telescope in the world, and it's co-owned by the University of California. Now, with these large telescopes, you have the incredible opportunity to answer some of the biggest questions that we can ask about our universe. We can ask about the origin of the universe. We can ask about the potential for life elsewhere in the universe. And we can also ask about black holes, which is my particular passion in life. So I'm going to start this lecture with a question, which is, how do you observe something you can't see? Because this is an essential question if you want to find and study black holes, because these objects have such strong gravity that nothing can escape them, not even light, so we can't see them directly. So the story that I'd like to tell you today is how we've been able to find a supermassive black hole at the center of our galaxy. And this has not only provided us with the best evidence to date for the existence of these truly exotic objects, but it also provides us with a wonderful opportunity to study the fundamental physics of black holes. In other words, how they warp space-time, and also to understand what role these black holes play in the formation and evolution of galaxies. Now, on our journey to the center of the galaxy, to prove that black holes exist, we first have to agree on what a black hole is. Seemed appropriate to leave a blank slide. So while black holes require relatively exotic physics to describe them properly, the way I would like you to think of a black hole today is an object whose mass is confined to 0 volume. So despite the fact that I'm going to talk about things that are supermassive, and I'll get to what that means in a moment, they have no finite size. What this actually represents, actually, if you think about density, which is just mass divided by volume, since the volume is 0, this quantity goes to infinity. And in physics, anytime you have a quantity going to infinity, it's known as a singularity, or it's a big red arrow saying you do not have your description of the physical world quite right here. Another way of thinking about this is black holes represent the fact that we do not know how to make 2 areas of physics work together. So we do not know how to make the study of gravity, which is what Einstein's so famous for with his theory of general relativity, so the study of things with lots of gravity. We do not know how to make this work with the study of quantum mechanics, which is the description of things that are very small. And black holes embrace these 2 things, so we actually don't know what a black hole is. We simply don't have the tools to describe it. But fortunately for me, there is a size that we can talk about and that's associated with a black hole. So just keep in mind that physically it has no finite size. But there is an abstract size that we can associate with black holes. This is known as the Schwarzschild Radius, or popularized by Star Trek as the event horizon. All right, so it's the last point that light can escape this object. So in other words, information cannot be communicated from the inside of this radius to the outside world. And it takes going at the speed of light to escape this object at this radius. So you can escape once you get inside. All right, now, it is also true that every object in the universe has a Schwarzschild radius associated with it. And what that means is that if I can figure out, or if one could figure out, how to shrink that object down to its Schwarzschild radius, then at that point, it would be forced to become the infinitesimally small object known as a black hole, because at that point, gravity overcomes all other known forces. So it has to collapse. So you have a Schwarzschild radius associated with you, your cell phone does, your neighbor does, anything you'd like to turn into a black hole. Turns out it's relatively simple to calculate. It only depends on mass. So to give you an example, if we could take the Earth and squeeze it down to the size of a sugar cube. Actually, somebody recently pointed out to me that's a rather old-fashioned notion, so we should say maybe a penny. It would be forced to become a black hole. The bigger the mass, the bigger the Schwarzschild radius. So if I were to take the sun and squeeze it down to the scale of, I had to put UCLA, I should put Foothill College, but down to a campus size, it would become a black hole. So not only does this define what a black hole is, but it actually gives you the structure of a proof to prove that there is a black hole. I need to show that there's a lot of mass inside a scale that is very small, ideally down to the size of a Schwarzschild radius. Okay, so I only need 2 things. I need to know a mass and I need to know a size. All right. Now, let's think, now that we've got the definition of black hole, let's think about where do black holes turn up. And it turns out that astronomers talk about 2 kinds of black holes. The ordinary black holes, as if there could be such a thing as an ordinary black hole, and the supermassive ones. As you might guess, they're really massive. So let's start with the ordinary ones. And this is actually a great demonstration of how science works. Sometimes it starts with an idea, the theory end, and that's the case with the ordinary mass black holes. This started with people thinking, astrophysicists thinking about what would happen at the end of a star's life. It were very, very massive, the most massive stars that we get in our galaxy. These are, for most of their lives, they're roughly 30 times the mass of the sun and larger. it was realized that when these stars run out of gas, what they're going to do is the outer parts are going to explode. And that's what we're looking at here. We're looking at the explosion. This is a supernova, so it's the outer layers of this star shooting off into the universe. And all sorts of exciting things happen, like the chemical complexity of our universe is generated in this explosion. But from the point of view of this lecture, what's interesting is that at the heart of this star, the inner parts of the star collapse down to become a stellar mass black hole, or roughly 10 times the mass of the sun. So those were predicted from theory, and now we have great observational evidence. We had great evidence 2 years ago, or many years ago, and it was even further confirmed with the gravitational wave detections that were recently announced, or roughly a year ago with LIGO. So that was observations confirming a theory. Now, the supermassive black holes are, the story is the opposite. It starts from observations. So the supermassive black holes we think are 1 million to 1 billion times the mass of the sun. So much, much larger. And in fact, what I'm showing you here is a picture that has a much, much larger scale as well. The last image, we were looking at a single star. Now we're looking at a picture taken with Hubble Space Telescope of the universe. And every single object in this picture is a galaxy, except one object, which is a star in our own galaxy. And each galaxy contains roughly 100 billion stars. So the scale is very different. And this is taken at optical wavelengths, which is what your eye detects. And the light that we're detecting here comes from stars, all those stars that we're seeing. And the suggestion from observations is that at the heart of these galaxies, there are supermassive black holes that reside there. Now, what was the observation that led people to suggest that this is the case? Well, it was observations of a class of galaxies known as active galactic nuclei, or AGN for short. Active galactic nuclei are exactly what the name suggests. They're galactic, galaxy centers, nuclei, that are very active. So there's a lot of activity happening from the center of these galaxies. I like to call them, they're kind of the prima donnas of the galaxy world. They're roughly 10%, they're very energetic. So what we're seeing here is a picture taken at radio wavelengths. So much longer wavelengths than the last picture. And what you see is the center of the galaxy, which is actually a very small scale where all the stars are, but emanating out from the center are these huge jets that are going at tremendous speeds. So we can calculate the energy, and we see that there's a lot of energy there. And that means that something very powerful has to be at the middle. Some central engine has to drive all this energy. The second thing that's unusual about these galaxies is that at the center, there's light, or emission, that we see in this picture that doesn't look like starlight. It doesn't look like starlight. It doesn't look like calm gas. It looks very energetic. And the interpretation was that what we're seeing is matter falling onto the black hole. In other words, light right at the event horizon. You could say that what we're seeing here are the dining habits of a supermassive black hole. And these black holes are, in these cases, are having a huge feast. So think Thanksgiving feast. So these have been known about for a long time, and the idea that maybe supermassive black holes are powering them is an interesting idea, and there's been mounting evidence for that in the cases of active galactic nuclei. And this gave rise to the question, do all galaxies, even the ordinary garden variety galaxies, have supermassive black holes at their centers? And this is an example taken from that picture, but zoomed, from the Hubble Space Telescope picture, but zoomed in. And it's a case that shows probably what our galaxy would look like if we could get out and look back. So our galaxy is a flattened disk-like structure. We have spiral arms. The sun, where we live, is roughly halfway out. So we want to know, do ordinary garden variety galaxies have supermassive black holes? Or you could say stealth black holes, or you could say black holes on a diet lurking at their centers. And if you want to ask this general question about supermassive black holes at the center of galaxies, certainly our own galaxy is a wonderful place, in fact, the best place to ask that question, because it's the closest example of a center of a galaxy that we'll ever have to study. The next closest galaxy is 100 times further away, so we have an opportunity to see our galaxy center in far more detail. So this is a picture that's taken on the slope of Mauna Kea in Hawaii, and that shows our view of our galaxy. So our galaxy is this flattened disk-like structure. We live in the galaxy, and when we look towards the center of the galaxy, we see that plane. So this is the plane of the galaxy. So hopefully you'll notice both the presence of light, the stars, but also the absence of light that runs through this. And this is because our galaxy, like most galaxies, is composed not only of stars, but also a lot of dust. Now, I'm from Los Angeles. I have a very good appreciation for what dust means, dust in the air. It's just like smog. Smog is dust particles that have sizes that are roughly the size of optical light, which means they're really good absorbers or blockers of optical light. 1 out of every 10 billion photons or light packets makes it to us at optical wavelengths. So if I want to see the center of the galaxy, optical wavelengths, optical astronomy is really off limits. So all the work that I'm going to present to you has been done at infrared wavelengths, as a wavelength where your TV remote control works at. So we're on a journey to the center of our galaxy. And if I want to prove that there's a black hole there, the best way or the most direct way to do this is to look at how stars move. Stars move under the influence of gravity, just like planets orbiting the sun. I can map out those, if I can map out those orbits, I learn 2 things. I learn how much mass is inside each star's orbit, and the size of the orbit gives me the region that I've confined it to, which are the 2 things that you need to prove that there's a black hole. I need to show you a mass, and I need to prove that it's confined to a small scale. Ideally, it's Schwarzschild radius. Okay, which means I want to get as close to the center of the galaxy as I possibly can achieve, which tells you, going back to the beginning of the lecture, why I wanted so desperately to have access to the Keck telescopes. So astronomers are driven to build larger and larger telescopes. And the reason is that there are really 2 campaign promises of large telescopes. The larger your telescope, and this is described, the size of your telescope is described by the mirror diameter. So your mirror, the collecting piece, it's like a light bucket. The larger your telescope, the more light you can detect, which means you can see fainter things. In astronomy, fainter things are more distant things. And because light takes a finite amount of time to get to us, that's like a history lesson. So that's a huge driver in astronomy, and in fact has been the primary driver in recent years. But there is a second campaign promise, which is the larger your telescope, the smaller the detail that you can see. Yes, so those are 2 reasons why you want to build large telescopes, and it's a second aspect that has been a real interest to me. Now I'm going to ask you a few questions. I'll repeat the answers because I know this is being filmed. So why is Hawaii such a great place to build telescopes? So I should have said it's in Hawaii. So why is Hawaii such a great place to build telescopes? High, it's high. I heard that one. Dark, I heard that one. No smog, don't like smog. What else don't I like? Oh, yeah, it's a great place to go on vacation. That's yeah. But let's see, it's near the equator, which means that there's a lot of sky that I can observe. So we got high. It's very, very high. So the top of Mauna Kea is 14,000 feet, which is wonderful because you're through most of the atmosphere, the Earth's atmosphere. The Earth's atmosphere is great for us. It allows us to survive, but it's a complete headache, and I'll get into this a little bit more for doing astronomy. So as you go up, you see the clouds below. In fact, all the weather, so if I think of Hawaii, when I think of a vacation, I think of tropics, wet, Astronomers don't like the rain. So you're above all that weather because you're going so high. Now, 14,000 feet, if any of you have been up to 14,000 feet, 14,000 feet is actually an interesting place to work. Your brain doesn't work too well up there. So there are all sorts of hysterical stories about astronomers. So astronomers who write down everything at sea level in order not to forget when they go up to the summit, only to forget the list. My personal story about this is the first time I went up there with a grad student, we had a debate. I'm not kidding. Our first debate up at the top of Mauna Kea, which was, what's 128 divided by 2? So it's a challenging place. And fortunately, because telescope time is very precious, it's $100,000 per night. So this is precious resource. You do not want to be mentally impaired. So today we can actually take our observations and control this telescope from sea level. Not only sea level in Hawaii, but also sea level at the campus. So every UC campus actually has a control center, which is wonderful. Now, it's high, it's also located on a volcano. Hawaii is a bunch of volcanoes. So this is a picture of Kilauea, which is one of the 5, which is the active one. Now, Mauna Kea is a dormant one, which means it's supposed to be inactive for at least another 1,000,000 years. Now, that's according to the geologist, and I have to trust them because I'm married to one. So hopefully that's the story on the volcanoes. Now, the other aspect that I think somebody mentioned is that that the view is very good, that the atmosphere that you have to look through is actually very still. We don't like a lot of turbulence because that also messes up our view. And so putting a telescope where the atmospheric flow is smooth, or what we know as laminar, is really important. So any island that's surrounded by a big body, which is by definition surrounded by a big body of water, has that wonderful attribute of very smooth airflow. So you'll notice that modern telescopes today are built on high peaks near big bodies of water. So the Andes in Chile, Mauna Kea here, or the Canary Islands, these are all wonderful examples of places that are good for astronomy. Now, somebody else mentioned the dark skies. This is critical for these telescopes. And it's an interesting challenge to find a site that's dark, dark, but also allows you to build some of the most challenging pieces of equipment, to be at the technological forefront. Dark skies and advanced technology don't usually naturally go hand in hand. So Hawaii is one of the few places in the world where you can find that nice combination. This is a satellite, a mosaic of satellite images of the world at night, and you can see where the developed world is in terms of high technology. So Hawaii is wonderful in the sense that there's been lots of ordinances put into place to protect or keep the skies dark. Okay, so Hawaii is a wonderful place for doing astronomy. So let's come back to the second campaign promise of the ability to see fine detail. And maybe to emphasize that point a little bit more about what that means. If you think about a painting, the painting that's done in the style of pointillism, that's made of dots, your ability to see detail or angular resolution improves as you walk closer to the painting. That's equivalent to getting a larger and larger telescope. So that's what we want to capitalize on. But for ground-based telescope, the problem has been the atmosphere. As I said, the atmosphere is great for us, but if you think about what's happening, we are looking at light packets, photons, that are coming from the center of the galaxy. These light packets, photons, have been traveling for 26,000 years to reach us. And in the last 30 microseconds, they go splat because they hit the top of the atmosphere. And so in that animation that we were looking at a moment ago, what you see is 5 bright stars. And if there were no atmosphere, each star would be the size of the smallest structures that we were watching dance around. But because of the atmosphere, they look like bug splat patterns. So that's the atmosphere, is that problem. Now, astronomers, a lot of my career has been driven by how do we get around this problem, right? Every challenge is an opportunity. And in this case, there are a lot of solutions to this. the problem of the atmosphere. One is Hubble Space Telescope. You get above the atmosphere. That definitely solves the problem. But from my perspective, where I want as high a resolution as possible to see the most detail, because I want to see the stars that are as close to the center as possible, this is a relatively small telescope compared to the Keck telescope. The diameter of this telescope is 2.4 meters. The diameter of the Keck telescope is 10 meters. So to give you a sense of that scale, that's like the width of a tennis court. And it's a factor of 4 bigger than the Hubble. But the power that goes into the kind of work that I do goes as the diameter to the 4th power. So that's 4 times 4 times 4 times 4. And because I'm not at 14,000 feet, I can do that math. And it's more than a factor of 100. And think about something that you would like to multiply by a factor of 100. Probably, or get more of, and you have a possibility of getting a factor of 100, you'd probably work pretty hard at it. So that's what has driven a lot of my work at Keck Observatory. So I've worked a lot on techniques for beating the atmosphere. And there's been a huge technological revolution in this area. So not only has the science progressed, but the technology that, that we can do this with has there's just been an absolute revolution. And so we've been surfing this wave of technology development, and it's been an amazing ride. This shows you an example. So the 5 bug splats that we were looking at before, if we take a long exposure picture as opposed to a 1/10 of a second, which is what was happening in that last picture, they look like big fuzzy blobs because of the atmosphere if you don't do anything. But if you correct for it, you can actually see higher resolution, and that's what this animation is supposed to display. And the little box is focused on where we think the black hole might reside. And you can see that without this technology, you don't see anything. It's just a blurry mess. But with the technology, you can see the stars that are the keys to the answer. And just to give you a little bit of sense of the progress, I want to show you where we started. I want to show you where we started. And for the students in the audience, I also want to make the comment that when I first started this work, this was in 1994, I was a new assistant professor at UCLA. I thought I had my dream job, and I thought I had a good idea. All I really wanted was a good idea to get tenure. So I put in my first proposal to get time on this wonderful telescope. And they turned it down. They turned it down. They said, not only will your technique won't work, will it not work, but even if it does, you won't see anything, which is a great reminder of just how hard it is to do something different. You know, the usual answer is no. But if you have a good idea, you got to stick with it. And fortunately, I had wonderful colleagues at UCLA that lent me some of their telescope time. And I remember the value of that telescope time. That is an amazing lend. Or share, and allowed us to demonstrate that the technique would work. So what we did was took very quick exposures, and we brought them back and stuck them in the computer and worked out what the atmosphere was doing versus what the star was doing. So this was sort of hardware cheap, computationally expensive. So all the work was in developing the algorithms. But nonetheless, it allowed us to see the stars at the center of the galaxy. So on the right is a little inset. Remember in that on-off picture, that was just a big blurry mess. And you can definitely see the stars. And this is one of my favorite movies. You can see them move. You do not need a computer to tell these stars are hauling. That means there is something at the center of the galaxy. Because remember, a lot of people who knew what they were saying said you shouldn't see anything. And the fact that they're moving, and you can probably find my favorite star in the galaxy, the one that's zooming around, its name is SO2. It probably needs a little bit better of a name, but that's what we know it as. Okay, so I love this, but in fact, and we did 10 years of this, but life progressed, as it always does, and it got better. It got better because the technology got better, and this is also a wonderful story of technology development, because it turns out that not only, astronomers are not the only ones who want to see through the atmosphere. Turns out the military also wants to see through the atmosphere, both up and down, and it just turns out that they have a lot more money than the astronomers do. So as the astronomers were steadily working away at ways of correcting for the atmosphere, at one point in the early 90s, the military basically said, we're not going to spend, the government shouldn't spend any more money on this development because we know how to do this. So it was declassified. And so that means that in the mid-90s, there was this huge leap forward in the astronomical community because there was a declassification. And so the astronomer's job was to figure out how to make this work. And this animation, where there have been a couple miracles happening already, like the telescope dome goes away, shows how that works. So we see we see the beam of light bouncing off the primary mirror and then going into the instrument bay. And we're going to look inside the instrument bay. So once again, we're going to have a little miracle happening. And that allows us to see the guts of this new technology, which is known as adaptive optics. And you're going to see two depictions of light. One is the beam of light, which shows you the direction of travel. And in a moment, we're also going to see a separate depiction, which is the wavefronts. And if there were no atmosphere, the wavefronts would be like flat pancakes. But because of the atmosphere, which is like a circus funhouse mirror, it distorts that wavefront. So you get something that looks more like Pringles potato chips. And the atmosphere is continually moving, so each chip looks different. And all the work happens up in the top right with a mirror known as a deformable mirror. And the job of this mirror is to take on the exact opposite shape, so the wavefront looks flat. So again, if you think about the circus funhouse mirror analogy, the atmosphere is doing one curve, and the job of the other mirror is to put the opposite shape so that you look flat or normal again. So you go from bug splats to something clean. So that overcomes the problem of the atmosphere. Okay, so amazing technology. Yay, good. And I should say, this is technology that was in large part developed, this declassification process by Claire Max at UC Santa Cruz. So this has been a huge UC project in many, many aspects. So on the left, we have this, the original technique. And on the right, we see the same field. And you can see that no matter how you look at it, it's much better. Therefore, it's in color. It's a factor of 10 deeper. You can, so you see stars at about a factor of 10 fainter. You can image these things more precisely, tell where the stars are. And you can actually take spectra, which is very important. And I'll get to that in a bit. Now, the key to this technology is not only the deformable mirror, but you have to look at something that tells you how to change that deformable mirror. So why in Hawaii, we tell all the local hotels, you can't do laser light shows because we don't like your light pollution. We do our own laser light show up at the summit. And so these lasers create artificial stars. They're tuned to a transition in the sodium atom, so they're called sodium lasers. And they take advantage of the fact that in our atmosphere, there's a thin layer of sodium atoms that are trapped up at about 90 kilometers. They're there because of, well, if you've seen a shooting star, those shooting stars are actually not shooting stars. They're meteorites that are coming down and burning up. And one of the outcomes of that is that there are sodium atoms that are deposited by the meteorites. And they get trapped in this small layer. And so we shine a laser up to that layer and make a star, an artificial star, anywhere we want in the sky. This was an evening where we were very fortunate to have observing time on both telescopes, both Keck and Keck 1 and Keck 2. And we were using the adaptive optics system on both telescopes. So it was like having two giant laser pointers saying, that's the direction to the center of the galaxy. If you don't have that, you can also look for the constellation of Sagittarius, which is the teapot, and it pours into the center of the galaxy. Okay. So this technology has allowed us to get much better images and spectra and to continue. So the whole business here is to try to measure orbits. This is the first time that it's been possible to measure orbits at the center of a galaxy. And what do these orbits tell us? Well, you can see there's tremendous progress here. So in fact, we're looking at a much smaller field of view area. I mean, before we were looking at a ridiculously small area from most astronomers' perspective, and now we're looking at a quarter of the real estate. But you can tell how these stars have moved. And now this is no longer, this is a model of what we've detected. When a star has been seen in an image, it's trailed by a dashed line. When it's spectroscopically detected, it has a solid line. But you can see SO2, my favorite star, has gone around all the way around the center of the galaxy on a human lifetime. This is rather amazing. Our sun takes 200 million years to go around the center of the galaxy. But here, at the heart of the galaxy, we've been able to discover stars that go around in 16 years. Now, what has that told us? These stars' orbits tell us the amount of mass, and the size of the orbit tells us the size of the mass that's inside it. The fact that these things are moving so fast tells you that there's a lot of mass. Before we started this work, we knew that there was 4 million times the mass of the sun inside a very big region represented by the circle. And you can see there are a lot of stars, there's a lot of stuff. So it really, no one could claim that there was a supermassive black hole at the center of the galaxy. It was just too big a region. So what this work has done has shown that there is 4 million times the mass of the sun inside a region that's 10 million times smaller. So in other words, it's an advance in the case for supermassive black holes by a factor of 10 million. It's shown that there's 4 million times the mass of the sun inside this scale that corresponds to the size of our galaxy. Now think about it. In our galaxy, we have one sun. And in this region, we have 4 million times the mass of our sun. So it's a tremendous amount of mass inside a very small volume. And that has provided us with the strongest evidence today for the existence of a supermassive black hole, not only at the center of our galaxy, but actually anywhere in the universe, which is rather amazing. So while it was the active galactic nuclei, remember the prima donna galaxies that made us think about supermassive black holes, it's now our galaxy that has provided us with the best evidence today. Right, so now where to? It turns out that this just keeps getting better. And so these orbits have now opened up a new and very powerful way for studying supermassive black holes. So we started off trying to prove that they existed, and now we have this unique opportunity to go forward and test, really to try and understand the physics of black holes and the role that they play. And this has made this project a key science case for advances in the future of adaptive optics and the next generation of large telescopes. So now we have a research institute called the Galactic Center Group, which is focused on the future science, technology, and education associated with this work. So let me just give you a little bit of a glimpse of where we're going. From a physics perspective, we really want to understand what is the complete theory of gravity. We really want to understand how is space-time curved? So we hear that expression a lot, the warping of space-time. And what this means is that when you get in a regime with a very strong gravity, space, which we think of, at least I think of in my everyday life, that we have 4 dimensions, time over here, and 3 dimensions of space over here. And in strong gravity regimes, these two things mix, and then at the event horizon become effectively undefined. Okay, so we know we need to go beyond it, and in fact, these orbits are probing a region of the curvature of space that has never been probed before. In other words, there's never been a probe of how general relativity works near a supermassive black hole. And these stars are offering the first opportunity. You need to wait long enough, in other words, to go around the orbit enough. In other words, make a complete orbit and then go through your next closest approach in order to get into the business of testing this level of physics. So SO2 is leading the pack. And in 2018, which is just around the corner, it offers us the first opportunity to start getting into this new era of testing general relativity. And there are many tests that we can do. In one, which is actually the first one we get to, we can look at how photons make it from the star to our telescope. Those photons have to climb out of the gravitational well. In other words, travel through curved space-time, and we can detect that curvature. And it's strongest near closest approach. So that's one test. It's called the relativistic redshift. Another test is to look at how the object itself moves through space-time. And because space-time is curved, instead of coming back to the same place, which is what Newton's version of gravity tells us it should do, it's going to overshoot, kind of like a kid's spirograph pattern. Okay? So the amount of curvature drives that what's known as the precession of the periapse. So that's what we're excited about from a physics point of view. You'd say it's 2018 or bust, and it's going to be an exciting year for us. The other aspect is looking at the astrophysics. How do black holes grow? How do black holes shape the galaxy in which they reside? And when we first announced our discovery of the supermassive black hole, and the early results, people used to ask which came first. Was it the black hole or the galaxy? It was like the chicken or the egg. And we had lots of explanations for one way or another. But it was a classic example of asking the wrong question, because as more evidence has come in to date, what's clear in other galaxies is that the mass of the black hole seems to be correlated with the mass of the central part of the galaxy, known as the bulge. And these are vastly different scales. So our understanding today is that whatever formed the black hole also formed the galaxy. They happen hand in hand. And that there's some feedback that happens that keeps the growth of these two things in lockstep over time. In other words, there's a feedback. So what's exciting from the galactic center point of view, the center of our own galaxy, is that this isn't the only place in which we can have enough detail to see this feedback process in action. And there are many predictions of this feedback. And this is one of the things that I love about doing research, which is almost every single prediction, given our new ability to see things, we've seen that every prediction that we've been able to test has been inconsistent with the observations. I like to call this job security. Okay, so the lore in astronomy is you should only show pictures and never spectra. But in fact, so much of the power of our work comes not only from images, but also spectra. I want to show you one. And spectra allow us not only to measure the speed of a star going along our line of sight, right? Pictures tells us the other two dimensions, but they also spectra also allows us to say what kind of stars we're looking at. Without them, they're just point masses. We can't say what kind of star it is. So this shows the spectrum of two stars. On the top, an old star, and the bottom, a young star. From my perspective, that's all I can do at this point. It's kind of like Hollywood. You're either young or old. And the buckets get defined by the spectra. So the spectra is the intensity of light as a function of wavelength. And there are these dips. These dips come from the properties of atoms in the surface of the star. And they basically tell you how hot the surface of the star is. And our models allow us to interpret that as being either old. And by old, I mean 1 billion years old. And by young, I mean 1 million years old. And to put that on human lifetime, or human scales for us to relate to, it's like a young star at 1 million years is like the human gestation period compared to the age, the lifetime of a person. So these are really just babes. So the prediction for these two kinds of stars are that the old stars have had a long time to interact with one another, and they, in a sense, know where the life of the party is. They're going to congregate around the supermassive black hole. So the anticipation is that there should be an entourage of old stars around the black hole, a dense concentration, what astronomers call as a cusp, lots of old stars. The prediction for the young stars is different. Young stars start from very fragile, large clouds of gas and dust. They're very tenuous. And to get star formation to happen, you need the gravity of that cloud or the particles to attract one another. It's called self-gravity, to collapse. But if you put it near a black hole is not a nice neighbor. It has what's known as tidal forces, which means it pulls more strongly on one side of the object than the other. We call this process spaghettification, or tidal distortion. And it's not a good place to put young stars. These are two young stars that I'm particularly fond of. They're a little older these days. But this spaghettification should prevent star formation from happening. So young stars are predicted not to exist at the center of the galaxy. Okay, so those are two concrete predictions we can make. So this is an animation that shows the orbital structure and the properties of stars that we're seeing at the center of the galaxy. The longer you wait, the more you can tell about the orbit. So as we wait, or take more, we're not actually passively waiting, we're taking more and more measurements and making those measurements better. We can get a better picture. So we're pulling back from the stars that we were looking at to prove that there was a black hole further back. And each star is color-coded. So the old stars, which should be plentiful, are orange. Where are the old stars? The young stars, which shouldn't be there, are color-coded blue or aqua. And that's the majority of stars that are there. So both things are the opposite of the prediction. And then from my point of view, the even more exciting piece is the things that we didn't think to predict, which are the pink things. Those are the unknown unknowns. And today we have explanations, or not explanations, we have the developing model for all of these things. Maybe let me share one developing story with the magenta stars. The magenta objects were originally suggested to be gas clouds heading towards the black hole. And as they passed the black hole, they were expected to disrupt. You can tell I didn't propose this. And that was an interesting idea. And it was predicted that lots of material should be dumped onto the black hole and should send the black hole into a high dining state. And astronomers were very excited about this in order to figure out what the dining habits of the black hole were. And in fact, this shows our galaxy's dining habits. The red light in there is a small amount of emission that we think corresponds to gas falling onto the black hole that's been happening ever since we've been able to look at it. Now, to say whether or not something has happened at the center of the galaxy, when this close encounter happens, it's been important to develop new techniques. So I also wanted to share with you that this has given us a wonderful opportunity to collaborate with our colleagues in the finance department, because it turns out the variations of the black hole's emission properties, the accretion properties, the dining habits, look just like the finance market. And if you're looking for evidence that something different happening, changing the state, it's really important to develop the right tools, because otherwise you can get fooled. So we actually collaborated with Francis Longstaff in the business school to develop new tools to tell whether or not something had happened. And in fact, absolutely nothing has happened. So we've had to come up with a different explanation. So my favorite explanation at the moment, which ties into many things, which is why I'm sharing this one piece with you, is that we think what's happening is that the black hole is interacting with these stars that are orbiting. But as we know from studies of stars near our sun, most stars are actually binaries, tight pairs of stars. And in fact, the most massive stars are almost always in pairs of stars. And if you put a pair of stars near a black hole, you get what's known as a three-body interaction, and the black hole basically drives that binary star to merge. When the merger happens, it gets enormous, and the black hole can shear off the outer layer, which is what's happening with those magenta stars. Now, I'm excited about this because I think it relates to some of the recent discoveries with LIGO. LIGO, the gravitational wave detector, has, like this experiment, opened up new ways of studying black holes. And like this experiment, has seen things that we just didn't expect. We're seeing stellar mass black holes that are much bigger than anyone had thought to talk about. And they're happening at a rate that seems much higher than people had anticipated. So the connection that we're developing is that the LIGO collaboration hadn't thought about binary stars in the connection with supermassive black holes. And yet most of the stars in the galaxy are concentrated to the center. So once you make this connection, it looks like one might be able to talk about, understand the large LIGO black holes as merger events. In other words, black hole binary star mergers. Now, in closing, I just want to remark that this animation that we're looking at here, while rather spectacular and has allowed us or unveiled a really extraordinary view of the center of the galaxy, we're just seeing the tip of the iceberg. Today, we only see the very brightest stars. We do not see a typical star. A star like our sun would be well below our detection limits. So one of the things that drives us forward in our desire to measure these orbits with much greater accuracy, which allows us to probe deeper into the potential well as to get to larger distances and deeper, is improvements in our adaptive optics system. Today, we use one laser, and in fact, that corrects roughly 50% of the problems introduced by the Earth's atmosphere. So what I'm going to tell you, of course, is if you launch a few more, that will get you all the way. And this is important not only for Keck Observatory, but because the larger your telescope, the smaller the fraction of light that will be corrected with a single laser. So as astronomers continue to be driven to build larger and larger telescopes, so in the world today, there are 3 large projects that are underway to get to the 30-meter scales. There's the University of California is involved in the 30-meter telescope, which is a UC, Caltech, Canada, Japan, China, and India collaboration. This is a $1 billion project. That is an enormous amount of money. But for context, James Webb Space Telescope, which is going up in space, that's a more than $10 billion project. And this is on the ground and much larger. So it's 6 meters versus 30 meters. To talk about these large telescopes, and I should have said there are 2 more. So there's the Giant Magellan Telescope and the European Extremely Large Telescope. So there are 3 such projects in the world being developed, all of which need to get to this next generation of adaptive optics in order to get to their highest angular resolution. I think this is going to be an amazing future. We're going to see sights at the center of the galaxy that we've never seen before. So this is a quick animation that shows where we are today, roughly, to what we expect to see in the era of the 30-meter telescope. Although I think that everything that we've learned from the current generation is to realize that we are undoubtedly going to see things that we simply didn't expect. So in conclusion, let me say that all of this work has been done with a really wonderful group of people that are part of the Galactic Center group. So if you want to know more, come check out our website. If you're a student and would like to come work with us, we have an internship program over the summer. And I want to thank you for your attention.
I would like to start just by saying this was one of the better presentations here, and I really thought it was superlative.
Thank you.
So I would just like to ask, black holes accrete matter and presumably gain angular momentum and have spin. And I was wondering if your observations are able to detect that at this point in frame dragging and such.
Well, in fact, one of the early excitements about seeing, when adaptive optics turned on, seeing the accretion emission that I showed you and that was variable, was the hope that you could see periodic signals coming from what's known as the ISCO, the innermost circular stable orbit. But it turns out that's been very, very difficult to prove. You also, in principle, should be able to see this imprinted on the orbit. So like the precession of the periaps, it's a higher order imprint on the orbit. I think that is well outside the realm of a Keck observation, but it's well within the realm of a 30-meter telescope observation. So I think that in the future, this may be possible. There are, for other galaxies that have the active galactic nuclei, people have looked at the gas that's close to look for evidence of the spin. And there has been evidence of the ability to measure the spin.
Great. Looking forward to reading about the learnings as they go.
Thanks. Okay, on the other side.
I'm wondering what the mass of the accretion disk is with respect to the mass of the black hole.
Minute. So we don't know the answer, but the amount of gas that is in that region is tiny. The larger, we think that there might have been much more gas in this region because in fact what I didn't emphasize, but you can see in this animation as it pulls back, that many of the young stars look like they form a disk-like pattern. And there's roughly 10,000 times the mass of the sun that we infer in that population. So perhaps at an earlier time, there might have been as much as 10 times more than that. So 100, 10 to the 5th times the mass of the sun.
Thank you.
Over here, right.
Okay, so from the picture you showed earlier, it looked like you'd gotten the maximum radius down to a little bit more than the radius of the solar system.
Mm-hmm.
So what's the Schwarzschild radius of a 4 million solar mass black hole?
Right. So it is 500 times larger than what we've achieved here. So it is, but it's many orders of magnitude better than anybody else has done. But if you wanted to be a skeptic, you've still got wiggle room. At an earlier phase in the experiment, when we were not quite as close, in fact, the particle physicists came up with an alternative idea, which is the idea that these might be fermion balls, so as an analog to neutron stars, so composed of much more elementary particles than neutrons. Neutrons. But now that we've gotten down to the scale of the solar system, that idea has been rolled out. So today, there's no theory today that will put 4 million times the mass of the sun inside that scale, but technically, you're still 500 times out from the Schwarzschild radius.
Thank you.
Yeah.
Assuming that there was a star, according to our line of sight, that went directly behind Sagittarius A, do you think would we be able to detect any sort of occultation or transit or even gravitational lensing of that star?
So gravitational lensing should absolutely be happening. And it's actually something that we are starting to look for. We did so in an earlier phase with the simpler technique. But the likelihood with that depth of observation was very, very low. With our current observations, again, it's more likely, but still quite unlikely. But with adaptive optics being improved, you should be able to get to the regime where these events start to become detectable. So they are physics tells you that they should be happening, and we're almost at the point that we should be able to detect them.
So if we pointed something like Kepler,
oh, great, thank you.
If we pointed something like the Kepler instrument at Sagittarius A, would we ever see something like a transit of a star going behind that black hole?
So actually, let me back up for a second, and because you've asked about gravitational lensing. So this is the idea that due to the gravitational field, you get a bending of light. So it's the curvature. It's actually the same thing as the curvature of space-time, effectively. And you get two images. You get a doubling of the image. That's very different than the occultation idea. So we will not see occultations, but lensing is something within reach.
Thank you.
Yeah, thank you. Over here.
Are there any discrepancies between the observed motion of stars near the galactic center and the predictions of general relativity and/or classical mechanics based on the assumed presence of a central black hole?
So we already see the deviations from the classical mechanics version of gravity. In other words, if we can't ignore general relativity anymore. For many years, we could. You couldn't tell the difference between Newton's version of gravity and Einstein's version. So today, you have to use Einstein's version. And our goal is to get to the next point where we can see whether or not Einstein's version of gravity holds at the next level. So stay tuned till 2018.
So in other words, you don't know yet?
We don't know yet.
Okay. All right. Thank you.
You're welcome.
Yes, I was just curious what your opinion is of how Hollywood tries to depict black holes. In particular, I guess the most recent would be Interstellar.
I think Hollywood did a great job of taking on the task of trying to translate black hole physics. I think they collaborated with physicists. Kip Thorne from Caltech was the scientific advisor to the project, and to the extent that one can still have humans involved, they did a fabulous job. You know, I should have made the connection, actually. They made my job as a scientist much easier because, in fact, I should have made the connection I often do when I give public talks. When we were talking about that gas cloud being pulled apart by tidal forces, this is the same idea that they were playing with when we observed on a planet the giant tidal wave on a planet near a black hole. That's due to the tidal forces. So that object that was being torn apart was like a giant tidal wave that got so extreme that the wave just lifted off the planet. So I think they do a great job. I think it's wonderful to get those concepts out into the general public. It inspires curiosity and it enables much better communication. Oh, excellent. Yeah.
What happens if you swipe out the sun for a black hole, maybe the size of Singer's X1 or something?
So if I could just swap out a black hole for the sun, and if I could keep the mass the same, so in other words, I didn't put a 4 million times the mass of the sun black hole, but I put a 1 times the mass of the sun, our orbit would be totally unaffected, because gravity only cares about mass, the mass at the center. Now, if I were to put a 4 million times the mass of the sun black hole in the center, we would go around a lot faster. We would probably notice a few other things about black holes. We would probably miss the sunlight. The amount of radiation that comes out from matter falling onto the black hole, if it was fed, would be also quite damaging to us. It's also interesting to ask, what if we were a planet, or what if we put the sun at the center of the galaxy? We would see suns traversing all over the place. It would kind of be like an exaggerated version of Star Trek, because then Star Wars. It wasn't. Here, I'm going to get myself in trouble. Didn't Luke Skywalker come from a planet with the 2 suns? So it would be a busy lit up sky. So it's fun to think about. Thanks for asking.
Getting back to a question you posed earlier, do all galaxies indeed have supermassive black holes at their centers? And if not, are there 2 populations of galaxies that are distinct?
So we think that the conclusion or the extrapolation from our galaxy is that if we have one, so does everybody else. We're ordinary garden variety, nothing special about us. But there is a debate about whether or not the lowest mass galaxies, because some of them, there are a few examples where there's no evidence. And so the question is, do they not have black holes today because they couldn't hang on to them, or because they weren't there to begin with? So that's a forefront question today. So again, stay tuned. Yes.
From a layman's standpoint, this black hole is right in the center of our galaxy, right? Right where this huge visible blob of visible light is. And I think you described it's impossible to see this through the dust. And we're lucky to see this through radio waves. All this is radio wave?
Oh, this is infrared.
Infrared.
So infrared.
So, but we're looking from the spiral arm into the center of the galaxy. Why isn't there all kinds of interference? Billions of suns and infrared things that are confusing you. How do you get to that simple little picture of all these little SO3s running around each other?
So I guess one of the important things that's important to say is that out here in the suburbs of the galaxy, stars are well spaced apart. So it's only as you go to the center of the galaxy that it gets more crowded, and it gets intensely more crowded at the center. So it means that when I take a very small pencil beam view, like a very small field of view, what I see predominantly are the stars at the center. And we, at this point, with all this orbital information, the motion information, can prove it. In our tracking of thousands and thousands of stars, we have a handful of contaminants. So these stars are really residing at the center of the galaxy because the density is so much higher. The density of stars at the center of the galaxy is 1 billion times higher than the density here by the sun.
Hey, thanks for being such a great role model. So my question is, what are black holes teaching us about the fundamental force of gravity? Like, we don't seem to really know, at least I don't seem to know what a graviton is in some of those theories.
So a black hole is teaching us that there are limitations. It's one of the signposts that Einstein's version of gravity is not complete. So, you know, in a sense, to say, you know, to try to say whether or not Einstein is right or wrong is probably not the right way to frame it, but that there's evidence that we need a bigger, more comprehensive view of the gravitational theory. Einstein's theory of general relativity can't explain what a black hole is. There are other pieces of evidence that are emerging in astrophysics that suggest, you know, maybe it's possible that we don't have our story quite straight, and maybe our laws of gravity might influence our interpretation today. So there are alternative theories of gravity that affect our interpretation of dark matter. There are those theories that also affect our interpretation of dark energy. So there are all these things that, you know, may be explained by a more complete version of gravity. So that's what we're looking for. And I think black holes are the most concrete evidence that we need to go further. So we haven't learned yet, but these objects in the universe offer the opportunity, the laboratory, for a more complete understanding of what is gravity.
So a black hole really points out, all right, we've got a problem in our, you know, we have an incomplete picture of our understanding of gravity. What are some of the kind of the theories that you think have more credibility than others on?
I have no idea.
All right, thank you.
We don't know.
Okay, so we can take 4 more.
Okay, 4 more. 1.
What is the diameter of the event horizon around the black hole at the center of our galaxy?
Okay, so here's a formula. I'll just tell you one. It's really to get the event horizon of the Schwarzschild Radius. If you measure the mass in units of mass of the sun, and you multiply it times 3, you have the Schwarzschild Radius in kilometers. So
do you know the mass?
So I have 12. So 3 times 4 million gives me 12 million kilometers. And that's roughly 10 times the radius of the sun for the center of our own galaxy.
Okay, thank you.
Yeah. Okay. 2.
I think this may be another frame question. Imagine a photon is emitted just outside the Schwarzschild radius, and then it heads off to the Keck telescope, and it gets redshifted quite a bit. And so it's emitted with a certain energy, and then when it gets to the Keck, it has less energy. What happened to the energy?
It's the energy it needs to climb out of the gravitational well. And to give you numbers, you can also describe this as an apparent shift in the wavelength. So if you think about the Doppler effect, this adds an extra shift, which is about 200 kilometers per second at closest approach.
And the question is, where does the energy go? It starts with a certain amount of energy. It arrives with less energy. What happens to the energy? Is that a frame question?
It gets converted to potential energy. So you take it from kinetic energy to potential. I mean, that's one way that's sort of like a classical way of thinking about it. I mean, yeah. Okay, it's a frame question. Okay. All right. 3.
what happens to dark matter when they travel through a black hole?
What happens to dark matter when it travels through a black hole?
Yeah.
So the great thing is if it comes inside the event horizon, it just becomes part of the black hole. It just adds to the black hole. So it gets bigger. That's how we can think about it. Thanks for asking that question. And last question.
The adaptive optics device that you use, the mirror that you use to adjust for the atmospheric changes, do you have to change that daily? Do you have to change that because the atmosphere is constantly changing? And how do you do that?
So I should have said, thank you very much for asking this question. So this deformable mirror is moving very quickly. So it has roughly 300 elements, and it changes roughly 1,000 times a second. So it's a part of the trick is being able to see something that's bright enough to tell you how to correct it, having the computational power to make those corrections fast enough. So in fact, the progress in computation is key to the progress in this adaptive optics system, because the larger your telescope, the more elements you're going to need. So you're just going to need a lot more computing power to have that calculation for so many elements happening that many times a second. The more lasers that you have, the more challenging the computations. So it's an amazing technology that pushes us forward on many different frontiers. So thanks for the question, and thanks for your attention.